So in combined footing, you're going to see here two columns and they sit on the same footing. I don't call this a mat foundation, but instead I'm going to be calling it a combined footing. Here's an example. I mean, there is no like new equation that I need to introduce here. It's going to be just the same concept in design that you're going to have vertical load and maybe some additional moment, and then you need to design the footing for when it comes to soil pressure below the footing. So in this case here, I have two columns. They are named here C2 and C4. And I have the bearing pressure is going to be 8,000 psf below the entire footing. Now, the problem with these two columns, they're coming close to each other. If these two columns had been far from each other by, let's say, a space of 30 feet or 25 feet or so, you would see here two separate footings, like a pad. It's going to be very similar to what we have seen here. But the problem, these two columns are coming very close to each other. And if I like here to draw the footing needed for each one of them, I'm going to see here's the first footing, let's say, and here's the second footing, right? You're going to see that there's just an overlap. And because this overlap is going to be happening, I'm going to say, why don't I just have it as just one footing instead of having two footings, which makes sense. The column just close to each other. For these two columns, I have been given for C4, which means the left column, I have 850 kips for dead load and 400 kips for life load. For C2, I have 680 and 320. To size the footing, I don't really need to multiply this by any load factors. So I'm not going to have the 1.2 dead plus 1.6 live or the 1.4 times the dead load. And instead, I can just add them up to find out the surface load. Here's the question, the footing dimension expected, and here's the distance from C4 to the left end. Just going to skip this section for now and see the analysis. What is that we need to do? So I took the previous schedule given the problem. It has axial loads in terms of dead load and life load, dead load and life load. And here I was able to find out the total load acting on the column as a surface load. No load factors, right? If you like to find out the pressure below the footing to do sizing of the footing, there is no load factors. But if you are trying here to find out the reinforcing, you need to find out the ultimate pressure, and in this case, it's going to be factored, which means a factor of 1.2 dead plus 1.6 life needs to be used. So in this case, just to size the footing, I need the surface pressure below the footing. Now here's the total force. Total force is going to be addition of these two values. It's going to be 2250 kips. It's going to be right in the middle. Here is P total. Now, if you like to have a good design or a kind of optimized design, you like to set this resultant here, which is a total force, to be right in the middle or in the mid or the dead center of this footing. Meaning, if this footing here is going to be 12 feet, this needs to be at 6 feet from each side, right? It's going to be the center of the footing. It's going to be right the location of the total force, P total. And also when it comes to this 24 feet, this is going to be right in the middle, which means from here to there is going to be how much now? I'm going to say 12 feet this way and 12 feet also this way. I said, okay. Now my understanding, the information given to me that the spacing between the two columns is 8 feet. I don't know how much is this cantilever. I don't know how much is that cantilever. Also, I don't know if 24 feet is going to be the right answer or not, and this 12 feet is going to be the right answer or not. That was not given the problem. That was actually the question. So the first question here is going to be the size of the footing. I see here a width times the length, width times length, width times length by the thickness. For now, I cannot really work on the thickness. So I'm going to pick whatever is going to come here with me as after I find out the required contact area. When you see here two columns and there's some spacing between them, I doubt it if a square footing is going to work with you. So I'm going to say forget about the 12 by 12 and forget about the 20 by 20. It's not going to work. Now, if you are able to put this resultant force between the two forces to put it right in the mid or the dead center of the footing, this is going to be great because you don't have here any moment effect. You're going to have a case like this. If I may go back here for quick, you're going to have a situation like this case here. You just have an axial load, which means something like this only. This is going to be perfect, right? You eliminate here all sources of eccentricity. We don't have here any moment. This is gonna happen if you can set the resultant force for these two forces to be right in the middle of, or the dead center of this footing. So if this is the case, the Q allowable is given here at 8 KSF, and the area needed is going to be equal to the total force divided by the Q allowable. So that when you take this 8 KSF multiplied by the area chosen, it's going to give you the total force that this footing here can support. So I said here, I have the total surface load, 2250 kips, divided by 8 KSF, and with that I have 281 square feet needed. This gives you the footing contact area between the footing and the soil is going to be needed. I cannot here do 12 by 12. It's not going to work. So most likely the 12 by 24 is going to be the best one is going to work with us. Now with this 24 feet, now I know the size. So I'm going to start here to draw my footing. I'm going to say 12 feet is going to be in this direction and 24 is going to be in this direction. And my understanding from the center of the footing, right? You're going to see here the total load, the resultant force. Now the other question is, where is this resultant force? Where does it happen? Because I need to figure out this cantilever length and this cantilever length. So you see what I call this? I'm going to call this to be cantilever. And this also going to be cantilever, right cantilever and left cantilever. I'm going to say first, I need to find out the location of this resultant force relative to C4 and C2. I know it's going to be in the middle. And I know most likely it's going to be shifted a little bit towards C4. Because the column load at C4 is 1250. The column load at C2 is going to be 1000. So most likely the force is going to be shifted a little bit that way. I said, okay. Let me try to figure out this total force where it happens, which means I'm looking for this X distance or X1. I need to find out this value here. Well, the way that you do it, you take the moment about this point load, about the center of C4. For the column loads only. So you say, well, C4 is actually running through the point that you're taking the moment about. So in this case, you're going to be, say, 1,000 times 8 feet. You have 8,000. And then you say, this is going to be equal to the moment coming from the resultant force. So it's going to be equal to 2250 times x1. Here's the equation. 1,000 times 8 is going to be equal to 2250 times x1. Now, here's the x1 value, turned to be 3.55 feet. So I said, well, 3.5 feet is a good number for construction. I'm not going to go there and make it 55 and end up here instead of ending up with 8.5. It's going to be, let's say, 8.45 feet. It doesn't make sense construction. So I'd like to go to a good number, right, in terms of inches. So are we good about this equation? We're clear about this? How to find out the location of the resultant force? You take the moment about this point load, about this column, the center of this column, and then you say moment due to the resultant is going to be equal to the moment due to the column loads. This column load is not coming to picture because I'm just simply taking the moment about the same point. So it's going to be 3.5 feet. Now, how much is this from the center of the column to that point? Anyone recalls the value? Yes? How much is this? I said, well, this needs to be L over 2 because it is my desire that I want this resultant force to be right in the middle of the footing. I'm going to say, okay, how about this distance here? I'm going to see this also is going to be 12 feet, 1/2 of the footing length. Right, let me take here 12 feet minus 3.5. It's going to be 8.5. How about this 12 feet minus how much? How much is this now? I'm going to say if this here 3.5, it means from this side is going to be 4.5 feet because 4.5 plus 3.5 is going to be 8. So this distance, right, from this center of the footing to the column, to the center of the column, in this case, this distance is going to be how much now? 4.5 feet. If this is going to be 4.5 and this 12, how much is this? Let's say, can someone help me here and do the math? From here to there, how much is this cantilever length? Yes? 12 minus 4.5?
7.5. 1.5.
Okay, and this give you the distance from here to the center of the cone. Okay, so I guess if I like to go very exact, I'd have used 3.55, but I cannot use here 3.55 for practical reasons. So I'm going to be going here to 3.5 feet. This means the location of this force is not really right in the middle of the footing. It's going to be shifted a little bit. But how much is the shift? How much is this eccentricity? If you like to call it eccentricity. You say the eccentricity equals, if you like to go and do detailed analysis, it's going to be 3.55 minus 3.5. It's going to be very small, 0.25 feet. This is going to be a very small amount that you can just ignore it. Not 0.5 feet, 0.05 feet. Am I correct? It's going to be a very small distance. This eccentricity here is almost nothing. And they have it written there. Look at the bottom here. Look at how much is eccentricity. Just to go exact. It's going to be almost nothing. Very small value. You can just ignore it if I want to. But now how much is the actual pressure below the footing? You can say actual pressure. You just take this total load, right? You divide by the actual contact area that you have chosen. So we're going to say you can take here. So I'm going to say here how much is the pressure. If I'd like you to solve for the pressure, I'm going to say Q equals, this is not Q allowable, this Q actual below the footing, is equal to 2250 divided by, I'm going to say here 12 times 24. And how much is the pressure in this case? I'm going to say here's the pressure. It's a 7.8 ksf. And again, how much is the allowable? I'm going to say allowable is going to be 8. So this give me the allowable value that I start to use. Is this the one? No, I'm wrong, I'm mistaken. This give me the right one. 8 ksf, which is right here, Q allowable. And finally, the one which happened right below the footing is going to be 7.8 ksf. This is good. It's going to be very good design because the actual pressure is really very close from the allowed pressure. So this is not over designed, right? And at the same time, it is safe because I still have some room here for any eccentricity that I did not expect. I'm going to say, do you mean that I still have eccentricity? I'm going to say, yes. Look at this. You have some eccentricity. So I said, okay, let's go here to do and refine my analysis. Just want to be sure that this eccentricity is not causing me trouble. So usually if I'm doing any design, I have this little bit of eccentricity, I can ignore it easily. I have no problem with this eccentricity here, 0.05 or 0.06, or even 10% of a foot, like 0.1 of a foot, it's nothing. 2-3 inches is not going to change my design in a case like this. But now I'd like to go here in details and be sure that this eccentricity is not causing me a problem. So what I would do here, I will try to find out the moment. And the moment in this case is going to be equals to this axial load multiplied by the small eccentricity that you're talking about. Now, how much is the small eccentricity again? It's going to be 0.055. It's going to be this number here. So here's the moment. Look at this moment. When you look at the number, you say, wow, this is a lot, 123 kfoot. So M over S, now when you look here at the S, now the moment is going to be running about this axis. And the H in this case is going to be the distance. From here to there is going to be the 24 feet. So S is going to be equal to 12 times 24 cubed, right? Divide by 12, and then you divide this by Y over 2, which is 12. Now, in this case, the S is going to be equal to BH squared divided by 6. I guess we should have it here. Yeah, it's right here. BT or BH squared divided by 6. So it's going to be 12 times 24 squared divided by 6 is going to be 1152 cubic feet. So I said, okay, here's S, and here's the moment, and M over S is going to be 0.1 ksat. Now compare the stress component coming from the moment and compare it to the stress component coming from the axial load. You say this is going to be much higher, which is very good. So in one side, I'm going to have 7.9, the other side is going to be 7.7. And how is that? I'm going to say this is happening because in one side, I'm going to say Q equals, I'm going to say here P over A plus M over S. And the other side, so I'm going to call this Q1, if you like. This is going to be here Q2 equals P over A minus M over S. P over A is going to be the 7.8. So at one time you add 0.1 to it, this gave you 7.9. At the other time you subtract 0.1 out of the 7.8. You end up with 7.7. So I was really concerned about this number here. I don't want this number here to go beyond 8 KSF. So I said, well, this is great. This little eccentricity is acceptable and is not causing the stress to go beyond 8 KSF, which is allowable stress. Any questions? We're good?
When we were calculating for x1, how come we chose that column C4 instead of C2?
In calculating of x1,
Yeah.
you can use the other column. Do you want to help me with this calculation?
Yeah.
Okay, I'm gonna call this x2. So let me draw here a new thing. I'm gonna say, okay, this is what I'm gonna be calling here x2. All right. Now let's take the moment about this column. What equation should I put in there? Tell me for this one. I'm gonna be taking the moment about C2. I'm gonna say the first moment is equal to moment coming from the columns. What value should I put in there?
1,250 kips times 8.
Yeah, equals.
Oh, I don't have my calculator.
2250 times x2. Can you tell me how much is this x2? Can someone help me, please? Amin, are you there? Can you help me with this? Amin? Amin?
Sorry, I'm not sure.
You don't know how to do this analysis? You cannot run this for us? You're not sure about what? Amin, are you still there?
Yeah, no, I'm just haven't been. I'm not up to date on this lecture yet.
Okay. Would you please stay focused with me, because you don't really need to know the previous lecture to be able to follow me here. I just started something completely new, which is this combined footing. And I'm coming here that I am put some simple equation. And I'm sure that many of you guys, you can just do the analysis, do the math here for me. And this is what I ask you to do. But it seems that you're not giving enough attention. I understand that that maybe you're doing something else. But please, if you stay focused with me, because you don't want to lose track of the following lecture and the following lecture and the following lecture, right?
Yeah.
Now, can you please look at the screen for a second and solve this for me? How much is this x2? Yes, Mr. Amin, go ahead.
Is it just 4.5?
Is it? Okay,
Oh,
thank
no,
you.
just looking at the diagram.
Okay, great. Did you just read it from the diagram, or did you do the math?
No, just the diagram.
So can you do the math?
Is it just you're multiplying by?
I don't know. Can you just look at the equation and do the math, please? Because I feel that I did here a mistake. Maybe I'm wrong.
Yeah, I'm not sure.
Do you have a calculator on you?
Yeah.
Right. I mean, you know that from time to time I need to put contribution and grades for people, and I need to give you a grade here for today's work. What do you want me to do?
Oh, I mean, it's 4.44.
Are you sure?
Yeah.
How did you do it? Tell me.
1250 times 8 divided by 2250.
Okay, great. 4.44. All right, thank you. All right, after we do x2, I guess I can assume this or round it up to be, you can say 4.5 feet. If now this gonna be here 4.5 feet, how much is left cantilever, the right cantilever length? I'd like to ask Adolfo. Are you there, Adolfo? Adolfo?
Yeah.
Yeah, tell me. How much now is gonna be the right cantilever length?
So
If
since
I'm
it's
gonna tell you. How much?
it's the midpoint, so it's 12 minus whatever your x2 was.
Okay, and the x2 is 4.5. Now how much is this right cantilever, Adolfo?
0.5.
It's gonna be how much again?
7.5.
7.5. Thank you very much. Thank you. All right. Did I answer the question about taking the moment about C2 instead of C4?
Yeah.
All right. Very good. All right. Excellent. Thank you. So now we're done with this exercise. I have another example here at which we have combined footing.
Professor.
Yes.
So you want the larger value for C? You go with the larger value?
For C,
Yeah.
what do you mean? I'm sorry.
So since the C2 is 7.5, you did your calculations based on C1 because it's larger, or?
I have two columns. I have C2 and C4.
Yeah.
I have taken a note about this point, not just because it's larger, just because I picked this point and you should be able to do it around this point or around that point. Just, usually when you have a beam like this, right, is something that we are used to. And I'm asking you to find out the reaction, right? What do you usually do? What you usually do for this beam with these two supports, you take the moment about the left support to all the forces on the right side. Am I correct?
Yeah.
It's just a habit of taking the moment about this point, right? About the left support. It's just a habit that if you look here at any structural analysis book, you're going to see that usually they say, well, this give you the first support, let me take the moment about this point. But nothing wrong if you're going to be taking the moment about this point. You're good. All right. Now, the following example here, I have two columns. And there's big difference in the column loads. I have here this 12 kips versus 2 kips. In this example, I have column loads that are kind of close to each other, 1,000, 1,250, and you see here the difference in the locations give you half a foot. Right? The location, this give you here 3.5 versus 4.5. So the center is shifted by only 6 inches. But in this case here, I have good difference. I have 12 kips versus 2 kips, and this is the reason that I made this example that way. And I give you all dimensions of the footing and the location of, or the right cantilever, the left cantilever is given to you, the spacing between the columns given to you, and also the column size. This is giving you 2 feet, meaning from here to there is giving 2 feet. So 1/2 is giving a foot, and this column here is 16 inch by 16 inch. It says also the footing width is going to be 4 feet. Now, footing width means the dimension perpendicular to the screen, this dimension there. And they say that this dimension here is going to be 4 feet. Also, they give me the unit weight of the concrete, meaning that it seems here I need to figure out the weight of this footing, right? Because when I give you this column load, the footing weight is not calculated out. But actually, in reality, if you're doing an actual design, you need also to consider the weight of this footing there in your analysis. And now they give me 2 points. They say this is going to be 1 point, one corner, and here's the other corner is going to be B. And they're asking me to find out the stress at A and the stress at B. And also they give me the allowable bearing pressure so that I can check one of these answers. Now here's the footing elevation, 12 kips and 2 kips. Contact area is going to be 40 square feet. How would I know that? I'm going to say I have here 4 feet for the width times 10 feet. This is going to be 40 square feet. And for the S, I'm going to say moment is going to be about this axis. So in plan view, this is going to be my footing. It's going to be in plan. the length width is going to be 10 feet and the width is going to be 4 feet. So S is going to be BT squared divided by 6. It's going to be 66.67 cubic feet. And this is going to be S about this axis. Now, I need to figure out the weight. And the weight I need to do it is going to be the weight of the footing and the weight of the soil above. So I'm going to say, where's the weight of the footing? And say it's going to be the weight of this concrete block. You can have here 2.5 feet by 4 feet by 10 feet. And also I need to figure out the weight of the soil right above it. So you see here, if you like to go detailed analysis, you need to consider the weight of this, if you like, called overburden, or this layer that you have used of soil above the footing itself. Also, you need to include in your analysis. So it has here an assumption that unit weight of the soil is going to be 120 pounds per cubic foot. Now look at the vertical load, total vertical load. Because now I'm going to have P total is going to be happening right here somewhere. And this total load equals 12 kips coming from this column, 2 kips coming from this column. So it's going to be 12 plus 2, plus the weight of the footing. So I'm going to say this is going to be the footing weight, right? This is going to be equal to the following: 10 feet for the length, 4 feet for the width, 2.5 feet for the thickness, and 0.15 is going to be unit weight of concrete. As it says here, unit weight of concrete is 150 pounds per cubic foot, meaning it's going to be 0.15 kip per cubic foot. So this here is going to be the weight of the footing. So I can point to it and say, this is going to be the weight of the footing. It's going to be all this piece. Now, how about the weight of the soil above it? I'm going to say weight of the soil is going to be 1.5 feet for the thickness, 10 feet for the length, 4 feet perpendicular to the screen, times 120 PCF, 0.12, and this is going to give me here the weight of the soil. Total vertical load is going to be 36.2 kips. So I can put it here, 36.2 kips. All right. Do I have a moment acting with this? I mean, do I have any moment applied like this moment here? I'm going to say yes. How much is this moment? I say, let me here figure out the eccentricity. Do you think that the footing weight is causing any eccentricity on itself? I'm going to say no, because the weight of this footing is going to be right in the middle. Now, how many forces do I have? I have 1, 2, 3, and 4 forces. So the first force that I have is going to be the weight of the footing. The second one is going to be the weight of the soil. The third one is going to be this column load. And the fourth one is going to be this column load. So I have here 4 forces. So if you want to find out the moment, you can just take the moment about the center. And taking the moment about the center is going to be the best option you have. You wouldn't take the moment about A. Because after you find out the eccentricity, you need to subtract 5 feet out of it. So what I'm saying is, why don't you take the moment right about this point here, which is the center of the footing? I said, fine. This force and this force is going to get canceled out because it happened right in the middle of the footing. You're going to end up with 2 forces. The 12 kips for the big column and the 2 kips for the small column. This location here is going to be a foot because this column here is going to be 2 feet by 2 feet. And this column is located at 2 feet. Total distance between the 2 columns as given the problem was equal to 3 feet. So, okay, now this moment equals. Now, which one is going to be larger, do you think? The moment coming from this column or the moment coming from this column? Yeah, say moment coming from this column is 12 times 1. Coming from this column opposite to this direction of rotation is going to be equal to 4 kip foot. Now, let's look at it more carefully here. Now, direction of this moment here is going to be what? Clockwise, 12 times 1. Subtracting, because it's going to be counterclockwise, it's going to be 2 times 2. You end up with 8 kip foot. It's going to be putting pressure on point B and putting some uplift or some tension on point A. So the moment direction here is correct, as it's shown. Okay. Now I should be able to do P over A and M over S. Now P in this case is going to be the total force coming from the soil and the weighting and the weight of the footing. And the moment is going to be just as calculated out here, causing pressure on this side, causing tension on this side. Let's say P over A, 36.2, total force, divided by the contact area, the 40. So now this is going to be the pressure, or this is going to be Q sub P, if you like. This is going to be the force coming from the pressure or the vertical force. Now, due to moment, I'm going to have this to be tension or compression, 0.12 KSF. At one point, which is point B, you're going to be adding this two pressure to each other. At point A, you're going to be subtracting because this moment here is causing tension and this force is causing compression. So what happened? F at A equals P over A minus M over S. Now take this, subtracting this is going to be equal to 0.785. The good thing that this value here, M over S, numerically is less than the P over A, which means I should be able to use this equation safely. I'm going to say, how about the pressure at B? Now I'm going to say here the pressure at B, just add the two values. 0.9 plus 0.12 is going to be 1.025. So what is this 1.3 KSF? I'm going to say here, part of this problem here, it says, first find out the pressure at point A, and then find out the pressure at point B. And then after that, this says the allowable soil bearing pressure is equal to 13 PSF. Now, what would you do? In this case, nothing is needed because when you look here at the maximum stress below the footing, it's going to be about 1 KSF. This is then 1.3 KSF, and nothing is needed. So what is the conclusion here? What is the lesson out of this exercise? What is the big difference between this analysis that I have done in this exercise and between this? Now, in this case here, the footing weight and any soil above it is just ignored for a reason. Some cases we ignore the weight of the footing, and some other cases we need to consider the weight of the footing and any weights above it. Sometimes the soil engineer is going to give you a value and say this is going to be the net soil bearing pressure, and sometimes they say the gross soil bearing pressure. I don't want to go into details on this, but what I'm going to tell you here, whenever I want you to figure out the weight of the footing, I'm going to mention this. I'm going to say determine the weight of the footing when you do the analysis, the pressure analysis on the soil. Now, also in this case, when I want you here to look at this, when I calculate out the weight of the footing and the weight of the soil, that was right in the mid-center. And we were not creating any moment. And it was really helpful to keep this footing balanced. Just imagine here the idea of reducing the vertical load, like what we have done in the previous example. Two examples before, what we have done, we start with some moment value, and then we give a vertical force, 600 kips, and then we reduce 240 kips, and this resulted in some tension on one side of the footings. And here, having the weight of the footing and the weight of the soil above it actually is helping you in your analysis, if this makes sense to you. Now, the other question I have for you, if you want to find out the moment, because on the footing, not this moment, no, I'm going to say, let's say that I cut here a section on this cantilever and try to find out the moment at this section to work on the reinforcing. You remember we are going to have some reinforcing here at the bottom. We're going to have some reinforcing here. It's going to be running across, right? In both directions. So now I want to do here this analysis to find out the moment at this section to solve for the reinforcing bars. This is what I need to work on. Now, do I need to include the weight of the footing and the weight of the soil, or I don't need to? I'd like to hear from you guys.
Yes, you have to include.
Okay. Let me draw this here for you.
Because it's a uniform load, and like a beam, if you assume it as a beam, then it's going to be the weight of the beam and also whatever, for example, additional dead load we have on top of that. So it's going to be a uniform load. I think we have to include it in our calculation.
Okay. We do something here real quick. Let's say this shaded kind of this orange color represents the weight of the footing and the weight of the soil. Okay. And from the other side of it, and this pressure, of course, is going to be coming downwards. And from below the footing, I'm going to have different pressure here, right? Is going to be in this column. So this pressure, the green one, is going to be going upward. Am I correct? And the orange one is going to be going downwards. Does it make sense, or does it make sense?
Yeah, that makes sense.
Okay. So if this pressure here, when I do the calculations for it, if I included this pressure, I would like to cut a section here and do the analysis to find out the moment and solve for the reinforcing. And once you cut this section here, you're going to say, I'm going to have here a total force, resultant force of all of this green pressure, subtracting the force coming from the top, which is this orange pressure. Does it make sense? Why? Because in this cantilever here, I have a force that's pushing it up, and at the same time, I have its weight, which is resisting the uplift force. It's going to be coming down. This is completely different from the standard beam that you used to work with. Here's a standard beam. Can I have here two supports? Can I have dead load and live load on top of the beam? And then also part of this dead load is going to be the weight of this beam. So what you do, you say here, dead load is going to be equal to the self weight of the beam plus any additional dead load, and then you factor it, and then also you add what? You add the live load. And all of the loads coming to this beam is going to be coming downwards. So in this case, the self weight is going to be added to all the other loads. But in this situation here, the dead load is coming against this load, which is pushing it up. This pressure on the soil is pushing this up, right? And this load is coming against it. So actually, if you like to calculate this and include as part of this green pressure, which is the pressure going up, you need to subtract it during your analysis. This is the reason that if you like to design a footing, when it comes to reinforcing, you can just ignore the weight of it and the weight of any soil above it. You're not really ignoring it. You don't want to double count it. You don't want to take it once when you do the pressure downwards, and then you figure out the pressure upward is going to be including this self weight of the footing, and then come back when you take a section, you're going to say, here's the pressure going upward, subtracting the weight of the footing. You don't want to spend the time and do this. So what you do, you say, let me just ignore it. If I can ignore it here, I can just solve for this section and find out the moment acting on this footing and do the reinforcing. Who's following me here? Who has any question on this fact?
Excuse me, this is actually based on the analysis. Actually, everything has been designed. Right now, we are going to check. But initially, we have to include it. Correct?
Now, when you were including it, you were just trying to size the footing to find out the width and the length.
Yeah. So initially,
Now,
we have to. But
okay.
afterward,
Yes. Afterwards, what do you want to do? Go ahead.
afterwards, because the system is in balance, so we can cancel those two out, and we just ignore it for simplification.
Okay. So in this case, actually, if you like to do the load on the footing to find out the reinforcing, you cannot really use the service load, right? You need to find out Q ultimate below the footing. Make sense?
Correct, yes.
And when you do the pressure under the footing as an ultimate, you do not include the weight of the footing. You can be looking at this equation that we did, right? If you remember this Q ultimate, what did we do? We do Q ultimate divided by the contact area of the footing to the soil. We used here P ultimate, and we did not include the weight of the footing. Look at this problem here. It says the column load, right? The ultimate axial column load is equal to 680 kips. But we didn't even try to figure out the weight of the footing, because the weight of the footing is going to be coming downward, and this pressure here is going to be going upward. So if you like to include the weight of the footing at the beginning is going to be coming downwards, right? To find out this pressure, you're going to subtract it again if you like to find out the moment at this section. So what we have done, we ignored it at the beginning and we don't really need to look at it. And ignoring it does mean that we're not accurate in our analysis, just mean that we'd like you to simplify the analysis. Anthony, are you there?
Yeah.
Any questions on this? Is it clear what I'm trying to say here or no?
Yeah.
Are you sure?
Can I ask you later?
Okay, so let me ask you. Conclusion of what I'm saying here. If I'm going to be designing a section and the reinforcing of the footing, should I include the self weight of the footing or I should not?
Can you repeat it again?
When I do here the reinforcing analysis, I'm trying here to design the reinforcing, right?
Mhm.
And I have two options. One option to include the self weight of the footing. Second option, excluded. Which one should I go, Anthony?
Include it.
To include it, are you sure 100%?
That's what I think.
Okay, all right, very good. All right, actually the answer is not to include it. If you are trying here to do reinforcing design, you do not include it. And this is what I've been saying, and Raman was chatting with me about it or discussing it with me. And then we decided at the end, we don't really need to include it if we are doing here foundation design in terms of the reinforcing. Now, again, the question to you, Anthony, if I'd like to do here the sole pressure below the footing to size the footing itself, do I need to include it or I should not include it? I'm trying here to
Include
size
it.
the footing to include it. Okay, thank you. Yeah, this time you're correct. Thank you, Anthony. Stay with me, please.
Sure.
Don't go away.
I am right here.
All right. I'm not going to be going much in this section. This is actually the third for slide set for the reinforced concrete foundation. Now, in our situation here, we have a footing exposed to axial load and moment, and I'm sure that you guys have seen these two numbers before, right? You say, yeah, I've seen this. I remember this footing. Actually, it's giving this footing of slide set of 12. Here it is. Let's give you this guy here. Oh, it's not here. So actually, let's give you the 113, which I'm working on right now. Which is this guy here. You see this problem here? This example is giving exactly this example, right? This is the one that we start with 600 and 720, and then we reduce the vertical load to 240, and we didn't like it. So I'm going to be taking this footing here. I'm going to say the surface vertical load is going to be 600 kips, and the surface moment is going to be 720 kip foot. So fine. So what do you need now at this time? You can say I have the column size. I have the strength of the concrete. I have the steel grade. It's going to be grade 60. I have the thickness of the footing. It's going to be 30 inches. Now I have this. And the question is, solve for the reinforcing. Now I need to find out the reinforcing at the bottom. Now, do I need to include the footing weight? Anthony?
Yeah.
Do I need to include the footing weight when I do the reinforcing? Yes?
Yes.
Do I need to include it? Okay, thank you. Thank you very much. So as it says here, when I do the reinforcing, I need to ignore the footing weight, not to include it. All right. So when you do the reinforcing, do not include the footing weight. You don't have to, because if you're going to include it once, you need to subtract it on the other hand when you do the analysis. So I said here, footing weight to be ignored for the reinforcing analysis. Let me add here analysis, right? All right. So I said, fine. Let me find out here the pressure on both sides. I said, well, I just determined this. Here's the pressure. You just did this in the previous problem here. And we ended up with, what was the pressure on both sides? I said the pressure on both sides here, I end up with 8 KSF and 2 KSF on the other side. So fine. Here's 8, here's 2 KSF. So I'm gonna call this FS1, I'm gonna call this FS2. What does it mean by FS1? You can say F is gonna be the pressure, or Q. Some people also would like to use the term Q, which is fine. And S would indicate service. And S here will also indicate service, because this pressure here, 8 and 2, is based on what? Is based on this service load, 600 kip, and the service moment is going to be 720 kip foot. This here assumed to be, because I don't have how much life load, how much is dead load, I don't have it at the ultimate level. I can just assume here a factor of 1.4. So when you don't know if you have dead load versus life load, you just assume 1.4 factor. So when do you use here a factor of 1.4? You can see here load factor when you are uncertain about the nature of the load. What does it mean by nature of load? Dead load versus life load. So when you don't know if this is going to be dead load or life load, just use a factor of 1.4. Just take the stresses here at the service level, multiply by 1.4 to get it at the ultimate level. Now the 8 would become 11.2 and the 2 would become 2.8. There's another method of doing it. The other method, you can just take this 600 kills, multiply by 1.4. Take this 720, multiply by 1.4, and then redo the analysis again, which means do P over A and M over S. You'll end up exactly with the same analysis. So I said, let me just here do this, multiply by 1.4, and get to the ultimate stress. We good? Any questions on the step here? Moving from the service stress to the ultimate stress? Just use a multiplier of 1.4 if you don't know the dead load and life load. The contribution, how much is dead load, how much is life load. But if the dead load and life load was given to you, so what you need to do, take the dead load and life load, multiply by their factors, 1.2, 1.6 versus 1.4. Do the same thing for the axial load and moment, and then redo the analysis. Which analysis? P over A and M over S, and then do the stress distribution. So it's fine. Now, what is the critical section now for a moment? I have here two options. One person is going to say, let's take it here. I'm going to be calling this to be section 1. The other person is going to be saying, let's take it here at section number 2. This is going to be face of column, and this is going to be the maximum moment that you can develop in the footing. Is going to be about this section. I said, well, I prefer this section here because you're going to have here bigger force than that force from this side. Look at this force here. It's going to be this one here, right? The integration of this, which means this volume versus this volume. So I'm sure this is going to be larger. This here goes to 11.2. This one here is going to be 2.8. By all means, I mean, I need to do the section right here. So I said, it's going to be my section. Now, the stress here is going to be the same for the entire width of the footing. I said, well, how much is the entire width of the footing? I need to figure this out for 10 feet. So this here is going to be the same pressure throughout the width of, say this here is going to be 10 feet. Normal to the screen. Okay, this is going to be a distance of 10 feet. Therefore, if you want to find out this force, right, you're going to be drawing this, let's say in 3D. It's going to be something like this. And also you're going to have a third line like this. Then you're going to be closing it this way. something like that. So now I'm gonna have here two forces. I can do it like one force, like this area of this trapezoidal, right? Multiply by the width of 10 feet. But the problem is gonna be the point of application. Where is this force is gonna be at for this trapezoidal? So what I decided to do is to split it into two forces. One force is gonna be this box. So I say this is gonna be this box here, right? And the other force is gonna be this triangle. This small triangle is gonna be the other force. So this force F1 is equal to what? Is gonna be equal to this distance from here to there, which is this x. Now this is simple because I know the total length of the footing. If you remember, I have it to be 12 feet, and I have the column is 2 feet in this direction. So I said, okay, I should be able to find out x. Now to take this x, multiply by the stress at this point here, 7.7, times the width, 10 feet. With that, you're gonna have one force located at x1, and this x1 is equal to x over 2. How about this x2? How much is this x2? The moment arm. You say this moment arm x2 is equal to 2/3 of what? Of x. Where's x? It's gonna be this distance. So this is gonna be at here at 2/3. This is gonna be the point of application for this triangular force. Now, how much is this F2? You're gonna say F2 equals, you're gonna say it's gonna be equal to this small height, and the small height is gonna be equal to 11.2 minus 7.7 times x divided by 2 times the width of 10 feet. Now I'm gonna have here two forces, two moment arms. I can take now the moment about this section. So the moment in this case equals, let's say F1 times x1 plus F2 times x2. Now with that, I have the moment about this section. Now I'd like here to see the numerical analysis for this. So I'm gonna say, okay, let's see here, this F1 and F2. First, here's x. How much is x? I say x, give you the total length of the footing. 12 feet divided by 2 is gonna be 6 feet. And this little piece here, which is 1/2 of the column width, is gonna be equal to a foot. So I'm gonna end up by 6 feet minus a foot is gonna be 5 feet. And then I can continue after this. I guess I will need to go now to the office hour. If you have any questions, please follow me to the office hour and let's chat there. And also, I need to meet with you guys to discuss your midterm. And it's gonna be one by one. I cannot have all of you in the same time, right? Because I'm gonna be opening your exam to show you your grade and the way I graded here for you, and ask you a few questions. So be sure that you come to the office hour to discuss it before we have the second midterm coming.
Excuse me.
Yes.
For the homework number 5, it is out of 20 or out of 10?
Not sure at the moment, Ramin, but it's gonna be out of 10, I guess. Hold on.
Yeah, but you know, initially you put it out of 20. So right now what you uploaded actually,
Okay,
I assume
I look
that
into this.
because